Well, good morning, everybody. As he mentioned, my name is Tim Canham. I work at NASA's Jet Propulsion Laboratory, and I'm going to talk to you about Mars Helicopter, which is a project that I'm working on right now. So go to the next slide. Oh, I guess I can push it myself. Here's a little movie that we can watch that is a little artist's rendition of what the project does. So if you go ahead and push the play button. So that's a nice creative video of what the kind of things we hope to accomplish with these kinds of vehicles. There's a link down there at the bottom of the page that links to a NASA page that talks a little bit more about the project. What you saw in the video there, aside from the animation, was JPL has a 25-foot solar simulator, and we used that for a lot of our flight testing where they're able to pump it down to Mars pressure, and then we can do our test flights right in that chamber. So you saw one of our test campaigns, a short video from there. So let's talk about the conditions at Mars. Obviously it's a long distance from Earth, so you can't have an operator here on Earth joysticking the helicopter. So the answer to that is that we have autonomous flight and landing. Secondly, the atmosphere is very thin. It's 1% of Earth, so you can't use the same flight dynamics that you can use on Earth. So the answer to that is that we have large blades, they're lightweight, very stiff, and we run the helicopter rotors at very high RPMs. Finally, it's very, very cold on Mars. You can get to minus 90 C sometimes during the night. So we actually have to have a thermal control system on the helicopter to keep it warm during the night so our avionics and our batteries don't freeze. So I joked to some of my friends that the helicopter is really a heater that occasionally flies. And also, we need to be self-sufficient with our power system. One of the most frequent questions I get, believe it or not, is a question to ask whether or not the helicopter uses the rover like an aircraft carrier to land and recharge. Nope, we can't do that. The rover wants us to stay well away. So we actually have our own solar panel. We have a panel that's mounted on top of the helicopter where we recharge between flights. That gives us all of our energy. The rover drops us off with a full charge, but from then on it's on us to get our own energy. So here's a picture of it, sort of a cartoon of it. You see our rotors are about 1.2 diameter. They're all made of carbon fiber with a foam core. Sometimes we give these blades to press people. We pull them out of a plastic bag, and the blade is actually lighter than the plastic bag. And we have a landing system consisting of these spring-loaded legs. We have, as I mentioned, that rectangular solar panel on the top. We have the fuselage, which has all the avionics inside. You can visualize it. It's about twice the size of a Rubik's Cube. And we also have batteries that are inserted inside that cube, so that whole cube in the middle is what's kept warm. We have sensors and cameras on the outside. Our total mass is going to be right around 1.8 kilograms, or about 4 pounds. And our rotor is going to run around 2,600 RPM. It's variable. Our blade tip Mach number, which hopefully there's some aero people who know what that means, but The blade tip Mach number, the speed at which it goes, is about 0.7. And here's a picture of our flight vehicle right there, assembled and put together. We've just finished our environmental testing with the rover, and we're getting ready to ship after the new year. So what about the avionics? The avionics, obviously, for this helicopter would have to be very lightweight, very powerful, and low power. We run our guidance loops on the helicopter at 500 hertz, but we also do feature tracking navigation at 30 hertz. So all this stuff has to happen on the processors that we're flying. So I put a picture over on the right of the world famous BA Rad 750 that so many flight projects use. It's about 200 DMIPS, give or take, the current iteration of it. And I'll show in a slide below what our MIPS are. The problem is that they are very heavy and bulky and consume a lot of power. So we don't really have an option to use traditional flight processors for the project. So we made the choice to mix the COTS parts with some core radiation tolerant logic. So we have a rad hard FPGA as the source, the core of the system. We call it the top of the system. It provides clocks, core power management, watchdogs, and it interfaces with the sensors in the motor system. It has its own motor control loop internally. It's an automotive grade TI microcontroller, and it does sort of the attitude control of the helicopter. And it's a pretty fast microcontroller as they go. It's about 400 DMIPS by itself. It's a dual lockstep processor so that it can self-detect faults in the hardware. And we actually have redundant copies. So if the processor detects failures in its own hardware or the software detects a fault, in the middle of the flight it can swap over to the other side and the other side can pick it up. And we use a cell phone grade ARM processor. I had a chuckle earlier when the keynote speaker was saying, well, we're really trying to get iPhones into space. Well, here's sort of one. It's not quite an iPhone, it's more like a Samsung Galaxy, but there you have it. It's very fast. It's around 30,000 DMIPS compared to the 200 DMIPS for the Rad 750. It's got lots of memory. We have 2 gigabytes of memory. But on the flip side, it's not as robust as obviously the space-rated parts. We've done a lot of, like I said, thermal and radiation testing on it, and they do pretty well, believe it or not. Sometimes the tiny feature sizes of modern processors really help you because there's not a lot of energy to liberate when you have an upset event. The things that we found were challenging were not so much the processor, but the analog electronics like power management that supported the processor. And finally, we have cell phone grade cameras that we use for the feature tracking navigation and just to take pictures. So we have a VGA grayscale global shutter camera that's pointing down that helps us with our feature tracking and navigation. And then we have a 13 megapixel forward facing color camera that we're going to take pictures with. On the right hand side there you can see a picture. I don't know if I have a laser pointer here. The red one? There we go. You see the picture of this Snapdragon 801. This is the drone development kit that we bought that's the basis for this processor right here. It's still got the plastic parts on it, and universities will take this kit and build their own drone development kits on it. So we stripped off all the plastic parts and kept the cameras, and that's our flight processor. So where are the different parts of this system? We really have 2 major computer systems, 2 major avionics packages. We have the helicopter itself, which when it's stowed before we deploy, is tucked under the belly of the rover and laid flat. It has a dust cover on it to protect it until it gets deployed. And then we have what we call the base station. That's a instrument payload on the rover that we use as a gateway to talk to the helicopter. And there was a whole development on the rover we call it the MHDS, the Mars Heli Delivery System. It's a whole motorized mechanical system that was designed to place the helicopter on the surface of Mars. So that, again, this is a picture of our system before we get deployed. As I mentioned, there's 2 major elements. There's the helicopter itself, which is the flying vehicle, it's solar powered. We're going to have about 1 to 2 minute flights given the energy density that we can pack into the batteries. And our nav processor does the the navigation part where we're tracking across the surface. It does the typical CNDH functions like telemetry, commanding, radio, power thermal management. And we're running Linux. It's not a real-time version of Linux, it's the Linux that came with the development kit. It's just really fast. So you've heard the expression that quantity is its own quality. We have a lot of processing power, so it helps keep up. And we made our design tolerant to slips as well, so that even though the OS itself is not real time, we can tolerate that. The base station is permanently installed on the rover. It has its own radio to talk to the helicopter after it's deployed. And then it also has its own communication channel with the rover, where it's used to transfer telemetry and pictures and other engineering logs that we generate. During the cruise and pre-deployment phase of the mission on the surface, it also provides the software there provides the logic for charging the helicopter. During cruise and pre-deployment, every few weeks we have to top off the batteries to make sure they don't get too low. Here's a cartoon of the architecture on the helicopter. This picture over here is the picture of our avionics cube. The circuit boards themselves are structural, so they're tied together at the corners. And that forms our fuselage. As I mentioned, it's a Linux Snapdragon 801. We have this rad-hard FPGA that acts as the core of the system. The rad-hard FPGA itself actually talks to all the sensors and stages them for these two microcontrollers, because there's a big switch in the FPGA that if there's a failure, it switches control from one microprocessor to the other, or microcontroller. So the FPGA itself is the pipe through which all the sensor information comes. And as I mentioned earlier, the FPGA itself has some motor control logic in it, sort of an inner loop. And here is the base station. Here's the box that the base station is in. And really all the base station is the avionics cards from the helicopter repackaged, so that it allowed us to reuse a lot of the hardware and software on the base station, because we're really delivering, in essence, 3 whole computer systems with related software for this project. It's not just one on the helicopter, 2 on the helicopter, and 1 on the space station. So the base station also has that same rad-hard FPGA, just with a different FPGA code in order to do the things the base station needs to do, and then it has its own set of power electronics for charging the helicopter. And then we have our connection to the rover, which does have a RAD 750 on it. That's how we communicate commands and data back and forth with the rover. So it's a challenge, because we had a small software team. We were really split into 2 groups. One was the guidance team, and then my team, which was the command and data handling and all the infrastructure, all the I/O, all the CNDH logic was on my team, and we really had at most about 3 FTEs during the whole project to work with. So we didn't really have time to write it from scratch. We really wanted a reliable code base, and then we wanted to use a flexible architecture that allowed us to have multiple test configurations, because we had different venues, different requirements, and different times in the project. So we wanted an architecture that we could reconfigure to meet those needs for those different venues. So we chose the F-Prime flight software architecture. It was developed at JPL, but it's open sourced on the NASA GitHub if anybody wants to take a look at it. It was used on previous projects. RapidScat was its first deployment on the ISS. And then Asteria is a CubeSat that's on orbit right now. It's in its 3rd extended mission, and it uses F-Prime. Some future missions. Yesterday, my colleagues from JPL talked about Lunar Flashlight and NEA Scout. And we have a future small sat instrument platform that we're working on that's based on the GR740 from Geisler. And also we're having a lot of collaborations with university CubeSat projects, because many of them like the fact that they can quickly deploy and use F-Prime. And some of them are using even Raspberry Pis for their flight processors, and it's easy to deploy something like F-Prime there. And so we have a core set of components that we reuse across many projects. So that was a good place to start for us. What about it? It's a F-Prime, it's a component architecture. It's composed of components, where all the behavior in the system is centered, and ports, which are the interfaces between components. I think the best way to think of this is sort of a hardware analogy, is you have boxes that have functions in them, then you have very predefined interconnections between those boxes that you cable together. So the ports are those interconnections. So those components are interconnected together to form topologies, which then we build into a binary, which we call a deployment. So those are that's the terminology we use for F prime. So the components are not link dependent on other components. The traditional C development styles, you have module 1 includes a header from module 2. So now your compile and link time dependent on module 2. And in some bad cases, module 2 might be dependent on 3, which is back dependent on 1. So you can get these nasty circular dependencies. The components are not link dependent on each other. They actually get connected at real time. Part of the initialization is stitching this topology together. So for instance, on Mars Helicopter, even though we had 3 different processors, we actually had 11 different deployments that we put together for various situations. For instance, our radio team wanted to go off and develop all the code, a component to talk to their radio, but they didn't need all the hardware that came with the flight system. So we just put them on a Raspberry Pi with a radio component, and they developed all their radio code off on their own without having to worry about, getting the system, the whole system, to do what they wanted. So here's a little cartoon. You have the component itself with the ports. This little state machine is just meant to say that there's logic in each of these components. And you see them interconnected into a topology. So at the core of the F prime architecture are these concepts. You have serializables, which are data types that are passed between components. And the reason they're called serializables is we can take those port calls and take the data and serialize it or marshal it or put it in a data buffer in some cases and ship it out to another computer or another task in the system. And then because it's a serializable, it knows how to, that type itself knows how to serialize itself, and then the other end to deserialize itself. So those are the types that are passed into the architecture. The port attributes themselves, they are the interface types. The types are passed to the callee, these types I mentioned up here. So ports have a notion of direction. It's not always the direction of data flow, because you may have a port that actually returns data. So it's the direction of invocation. You can optionally return types, as I mentioned. Now the component attributes, they specify what the threading model is for the component. You can have what we call a passive component, which has no threads or no message queues. You can have a queued component, which adds in message queues so the ports can dispatch messages if they like. And then the final level is what we call an active component, which has a thread and a message queue. So all the messages are dequeued on the thread of that component. And we also define all the ground interfaces there. So the component, at the component levels, where we define all the commands, all the telemetry, parameters, and then at JPL we have something called EVRs, or events, sort of discrete events that you can track. Those all are defined at the component level. So when you attach a port to a component, you basically tell, by the component specification, you tell how that port is used. So the same port in one component can actually dispatch a message onto the message queue, or it can call the user's code directly. So the development pattern is that the autocoder, when we write XML to specify all these interfaces, the autocoder actually generates a C++ base class for us, and then the base class has virtual functions that are defined that the user will override in a derived class. So we did virtual functions so that if a developer forgot to implement their function, it will actually just fail to compile. So as I mentioned, we define the components and interfaces in XML, and then the developer writes these C++ derived classes. Now, one of the big features about the F prime architecture and the autocoders that are delivered with it is that it actually generates unit test code to go along with each component. In essence, what it does is it generates a second component that has counterpart ports to the component that you're actually testing. And it generates helper functions within that component to do things like issue commands, check telemetry histories, and initialize the system. So we spend a lot of our time when we're doing F prime development writing unit tests with these counterpart components. And my colleagues yesterday mentioned that we're really experimenting now with new methodologies in those unit tests with helpers within those unit tests that will do random test case generation, the rules-based checking that he talked about. There's a lot of progress being made there. So in our system, since all the components are defined, but they're not connected until the topology is designed, typically you have an architect in the system who will define the whole topology and actually interconnect them. They'll be in charge of defining the XML. The XML also, you can use the XML to define the topology itself. The architect will define that topology and interconnect them. We also ship a basic ground system with it, so you can actually have this ideal of a project within a single laptop. So you can run the system. The demo that you can download from the NASA GitHub includes that ground system, so you can run on Linux and have a little demo app up within an hour or so that you can run and exercise the commands that are in the demo. So for helicopter, here's a little cartoon of all the different modules, and it really shows how we were able to leverage these components across our different deployments. So here's some color coding about what each of these modules means. So we had this set of F-prime core components that we're using across multiple projects, and you can see it made up the bulk of the helicopter. The nav processor is the Linux processor that I mentioned, makes up the bulk of the nav components and an even larger proportion of the base station components. So on helicopter, we wrote some components, and because there was shared hardware, we were able to share a number of those components between those two deployments. And then finally, for helicopter, we had some unique, just because we had unique hardware, we had unique components that were written for the helicopter and a set of unique components that were written for the base station. But you can see there's only 3 really for the base station. Everything else was reused between the two processors. Now the flight controller, it was very unique because we didn't have an OS there. F-prime does not require an underlying OS. You can use it, but you're not required to use it. So we had a number of, in essence, passive components that didn't require threads or message queues that we ran on bare metal. We essentially had a 500 hertz cycle where we waited for a GPIO to change state, and then we'd run one cycle, spin on it, run another cycle. And that's how this flight computer would talk or would execute. We have a UART that's between those two where we would send at a high speed, we would send state back and forth. So summary, the use of COTS hardware really allowed us to quickly implement the Avionics package, not packet, I was typo. But we had a backstop of reliable flight parts that we could use, and we were able to get the performance that we needed out of that, which wouldn't have been possible with conventional flight hardware. And the use of F-prime as an architecture allowed us to leverage a lot of work done by other projects, so we didn't have to do that all over again. Also, the flexibility of F-prime allowed us to support a whole number of venues and different functions within those venues. So F-prime is available as open source. So if you download F-prime from the NASA GitHub repo, much of the code there is the code that we're flying in helicopter. So if there's any questions, I can take them now.
So F-prime, it seems like everything that you've done, you could have implemented in any sort of system, including CFS or any one of the other ones. Convince me why F-prime.
Well, F-prime, so there's a timeline, there's a phasing aspect of it. Is F-prime, we started to develop it back in 2013 when CFS was sort of an internal NASA thing. And we like the F-prime model. It's a point-to-point architecture, so you're interconnecting components. And I'm saying this, I'll freely admit, without digging into the guts of CFS, but it's a publish-subscribe architecture with a message bus. So at some level, it's good in that it's a plug-and-play architecture, right? You can add or remove things dynamically. But at some level, I believe it has to be doing some kind of a, when you do publish-subscribe, you're saying, do you want this, do you want this, do you want this, do you want this, right? So over time, our flight systems, we tend to know what the configuration is. It tends to be static. What sensors we have, what software modules we have. And so we just felt that this embedded component architecture was good for our purposes.
So one more question. I saw his hand go up first, so let's get him, and then we need to go on break.
So first off, very cool project, very cool architecture. One question, what BSP are you using for TMS 570?
So what we used was TI provides this development environment, and we basically use their compilers. So it's not a BSP per se. They have a tool that generates code based on what devices you have on the microcontroller and how you can configure them. It's a GUI-based tool, and we just generated that code, and then we basically added our own code on top of it. Since there is no OS to speak of, right, we just use TI's tools to do it.
Okay, thank you.